Hello everybody! In this video, I am going to discuss the idea and phenomenon of superposition, as well as the skill of sketching and interpreting the superposition of pulses and waves. So our central question is about how multiple waves interact. We've studied the properties of individual waves and wave pulses. So how do they behave in different conditions? In particular, what happens when two waves meet in a medium? We can answer this question primarily with the idea of the principle of superposition. That is, the total displacement when more than one wave is at a particular location is equal to the sum of the individual displacements contributed by the individual waves. This formal definition, by the way, is something you need to know and be able to explain. You do not need to memorize that exact phrasing, but you should know the idea. So to understand this, we're going to consider two wave pulses on a string. One wave pulse will be moving to the right with amplitude A. The other wave pulse will be moving to the left with amplitude A. What happens when they meet? You might think that they bounce off each other. You might think that they add up or cancel out. You might think that they somehow affect each other. And the answer can be acquired by applying the principle of superposition. The idea that at the point where they meet, the total displacement where that wave will be the sum of the individual displacements contributed by the individual waves. So our left wave has an amplitude A, our right wave has an amplitude A. So when they meet, they simply add up to an amplitude of 2A. Afterwards, both wave pulses simply continue on. So there's a very deep sense in which they did not affect each other, but they did affect the medium in a different way when they both reached the same point. Okay, so both wave pulses contribute to the displacement of the medium at that point. We can see a different version of this or another application over here. If we have one wave pulse traveling to the right and one wave pulse traveling to the left, but the wave pulse traveling to the left is displaced in the opposite direction, okay, downwards rather than upwards on the screen, then we can ask the question, what happens when they meet? And our answer is that the total displacement will be the sum of the individual displacements. But in this case, the amplitude of the left wave is positive, that wave pulse is displaced to the left, and the amplitude of the right wave is negative, that wave pulse is displaced downwards, And so when they meet, they cancel out. They completely cancel out. You have positive A from the left wave pulse and negative A from the right wave pulse, and then they continue onwards as they were before. Okay, and so the downwards wave pulse is now moving to the left, and the rightwards wave pulse is now moving to the right. And you can see that means they did not bounce off each other. They did not reflect. Ironically, then, we have a particular terminology for how they interact when they are in the same place at the same time. And we call how they interact interference. When they add up, as in case A, we call that constructive interference. And when they subtract, as in case B, we call that destructive interference. If they add up perfectly, we call that perfectly constructive interference. That gives us a maximum of 2A. And when they are perfectly canceling out, we call that perfectly destructive interference. Notice that the principle we use to get our solution to this problem is the principle of superposition, but what the waves actually do is called interfering. They interfere with each other, and the irony is that they don't actually affect each other. All right, so two more quick applications of this principle. One is to a slightly more complicated situation with wave pulses. And to understand this, we're going to use the example of these two rectangular wave pulses with different amplitudes. Notice that this would be really hard to produce in person, but it serves the point of showing us how we can apply this principle of superposition. So consider this left-hand wave pulse, okay? I'm going to color that wave pulse blue, and the right-hand wave pulse. I'll color that wave pulse red. And the question is, what happens when they meet? Well, there are different times. We can consider the time when they're completely overlapping, but the first thing that happens is that they partially overlap. And when they partially overlap, we can see that the superposition, principle of superposition, tells us that at any point along the wave, at a particular location, the total displacement will be the sum of the individual displacements provided by each of the wave pulses. So at this point right here, the only wave that is contributing to the displacement at that point is the blue wave. And so there is a displacement exactly equal to the amplitude of the blue wave. But in the center, those two wave pulses overlap. And as a result, the resultant amplitude will be equal to the amplitude of the blue wave plus the amplitude of the red wave. So at this point right here, blue plus red is equal to the final amplitude. Okay? Whereas at this point right here, the blue wave the blue wave has not yet gotten to that location, and so the amplitude is only due to the red wave pulse. Notice we can analyze the whole situation where we assume that the red wave pulse is quote unquote on the bottom of this particular overlap. And the result will be the same. So this is entirely blue, and then this section right here will be blue, and the result is the same. Okay, they then continue onwards. When the overlap is complete, the total amplitude is equal to the amplitude of the red plus the amplitude of the blue, and I'm just eyeballing it here, but you get the idea. And then they continue onwards. Our second important application will involve two full traveling waves, okay? Two full traveling waves at a particular moment in time. So we have a red wave traveling here as well as a blue wave traveling. And we can ask ourselves, what is the displacement at any particular point? So how do they superimpose? How do they interfere? We apply the principle of superposition, and we can apply it at every point. So let's take a simple point at first. Let's consider this point right here. Well, the red wave contributes an amplitude equal to this height, and a blue wave contributes an amplitude equal to the same height at that point. And so if you add them up, that will equal the amplitude of our resultant wave. And that means that this green wave is the resultant wave from the superposition of the blue and the red waves. Let's try another point, okay? How about this point right here? Well, at that particular point, the one currently indicated by the green dot, we can see that the resultant wave is 0. So we're getting perfectly destructive interference. Let us examine why that is. So if I go up here to the same point on the blue wave and down here to the same point on the red wave, I will discover that the amplitude of the blue wave is exactly equal to the amplitude of the red wave. Oops. The red wave, and therefore they cancel out completely. And let's pick another sort of interesting point here. How about this one? Okay, at this one, we expect the red wave, because it's at 0, to contribute 0 displacement. And so the blue wave should be the entirety of the displacement for the superposition of both. And we can see that this point where the red wave crosses the horizontal axis, that time axis, at exactly that point, we can see that the green wave, all right, involves or is exactly the same amplitude as the blue wave alone. And so superposition can be used to find the resultant wave at any point in space or at any point in time. You simply add up the contributions of the individual wave and you get the resultant superimposed wave. And this phenomenon in general is called interference. When the waves add up, it's called constructive interference, and the waves subtract, it's called destructive interference. This is true for two-dimensional and three-dimensional waves as well, which we will address at a later point in time.